Now the record is on. So what we did the last time is that I demonstrated how things would be carried out from the, here is the local stiffness matrix of member 1 with the code on it. So the code says that this will go on into the first row, first column of the global stiffness matrix of the entire structure or the system. This comes here. See the first row and the second column that comes here. Second row, first column, so it's here. Second row, second column, it's here. So this is, see, a portion of global stiffness matrix of the structure from member 1 only. Now we can repeat this for all the 5 members, and then we're going to have the global stiffness matrix of the entire structure. So I have this for you. This is what we did for member number 1. So I still somehow call it element in the old time. So when you look at member number 1, that is the components, right? Notice that this matrix is 4 by 4 because it's the stiffness matrix of the member. This is member stiffness matrix. Okay. Now with the code, it says that this one comes here. So essentially, I can write like this. I think it's easier for me. Or you can just memorize and then, okay, put this in the first row, first column, and so and so. Now, when we move to member number 2, remember the code here says 3, 4, 5. So I put 3, 4, 5, 0, 3, 4, 5, 0 here. So essentially, this says that this will not go, right? It's 0. You can just cut them off. And this will go into the designated position in the global stiffness matrix of the structure. Or I can just rewrite this as this. See? 3, 4, 5. No, I shouldn't point it like that. 3, 4, 5, 3, 4, 5, 3, 4, 5. So this is the contribution for member number 2. Okay, this is the contribution from member number 1. And we go back again to the code. This is for member number 3, is 1, 2, 3, 4. So everything goes for member number 3 because member number 3 is just hanging in the air, not attached to any support at all. So for member number 3, everything goes. So, but remember, this is member. So it's a 4 by 4. But the global stiffness matrix of the entire structure is a 5 by 5. So this will come in a shape like that. So 1, 2, 3, 4, they all come, but the matrix of the structure is 5 by 5, so we still have 0. Okay. Now for member number 4, the code says 5012. So it's getting a little bit tricky now because the way we define our local node 1, 2. So for this, it's that. Right? Okay. When you see 0, you can just eliminate it. Because, you know, it means that all these components will not go. So this one is, say, I'm sorry, that's a wrong row here. Okay. So first row, first column, it's this one. Okay. And then second, so this one go to the top left corner. You can see that, right? And then you add the 5th row and then the 5th column. And so for member number 4, it looks like this. See, 1, 2, and then the 5th row and the 5th column. And for member number 5, the code is 0034. So it's pretty simple. That's it again. 0, 0, 3, 4, 0, 0, 3, 4. So all this just go. Okay. So it becomes like this. I kind of prefer this because you can actually use a calculator to write the metrics like this and 5 of them and then add them up. Then in the end, you're going to get the result coming from this. So it's the same, but this, I wrote this because it gives you the picture of how the assembly is made. Because this one comes in here, right? This one comes in here. This one comes in here. This one comes in here. And then when you look at member number 2, it's 3, 4, 5. So, you know, I use the gray designated. Okay, this is that, and then that. But say calculation wise, doing the global stiffness metrics in this fashion, you know, the one that you see here, this one, you're going to make mistakes, you know, more than doing this. But it depends on what you like, you know. In the end, you must understand that this stiffness metrics must be symmetric. That's the key. It has to be. Otherwise, you cannot find the inverse. Okay, so that's how we assemble it. And in the end, keep in mind that the matrix of the member is 4 by 4. You assemble this and you're going to have the matrix of the system with the size in accordance with degree of freedom. So it's just one important step here to put the global stiffness matrix of each member into the global stiffness matrix of the entire system by using the code metrics. It's like playing games, really. So now you have the global stiffness matrix. It means that you can now solve the structure. Okay, so that's it. Any question? You can ask. Pardon me. Yeah, go ahead.
Could you go to the element 4 again? Element 4, I will find. Yeah. Where is K4 11 K4 11 of the previous one?
K4 11.
Yes. For the assemble, when we cut it out, right? Element 4, the first one will be K4 11, right? Yeah, and
yeah, let's call it K11, okay? K11,
yeah, K11
element 4.
Okay.
It's gonna go to the 5th row here.
It will be we change the log. Oh, okay, I see. Got it.
It's a 5, 5. See, so it comes here.
Oh, okay, I see.
Good.
The number that show it will be location, right?
Yes, yes, exactly.
Okay. I see.
So it's like playing games, you know. So you get a hang of it. Just you see, let me wrap it up. For K11 of element 4, you have the code 5, 5. So it says it goes to the 5th row, 5th column of the assembly. So it comes here. Simple as that. Like this. Let's say, give more examples so that you see a better picture. So this is the K33 of element number 5, or member number 5. It says 3, 3. So this one comes to 3rd row, 3rd column, like that. See how easy that is? And this one is a little bit more complicated because of this. See, this one, for example, it's a 5th row, 1st column. So this guy, 5th row, 1st column. So it has to be 5th row, 1st column. See that? And that 5th row, 2nd column. So it comes here, like that. It's kind of fun, actually. And very easy. It's just one sad thing that always happens, that some students always mess up the trigonometry, because these k's are going to come from this. Here. This is the essential part. Global stiffness matrix. And it's pretty sad because now it's like, it's the easiest thing in the world, because when you look at the matrix and you look at the member, say, let me try to add the note here, maybe. Okay. I got a very good teacher, good math teacher. I owe him a lot in my life. He said, okay, this is the quadrant system. Okay. If your vector is in the first quadrant, sine is the x value, right? That's a sine. That's a cosine, right? So you know the sine is x, cosine is y. So it's if your vector is in the first quadrant, it's plus plus. If it's in the second quadrant, what's happening? Sine is minus, cosine is plus. If it's in the third quadrant, both become negative, right? And if it's in the fourth quadrant, sorry, it's negative and positive. So to tell where your values are, you just need to look at your vector. Because say this is 1, 2, right? It points towards 2. So if you 1, 2 is like that, it's plus plus. This is 1, 2 like this. That's 1, 2, right? That's 1, 2. And some students always mess up the value. I just don't know how to help them anymore. Because that's how your zeta is counted. Right? Starting from this point and then traveling like that. So if this is the local coordinate 1, 2, the angle will be something like this. Correct? Let's see. If you count, if you use the local designation like that, that's your angle. And remember, from high school, because you can look at the quadrant, you can see that this say sine pi over 2 plus theta is equal to minus sine theta. Or no, sorry, it's sine theta, not minus. See, I have to look at the quadrant because I don't really remember this, but I remember the quadrant. And cosine pi over 2 plus theta, this is minus cosine theta, something like this. And every year there'll be some sorry students who mess this up, and this is high school math. So I'm not obliged to talk about this. It's high school math, right? And I hope, sincerely hope, that all of you who are here should not mess this up. Not here, not now, or anytime, in the homework or in the exam. All right. Or if you want to, another one, if you want to rotate your angle from here, oops, let's change the color. If you want to rotate your angle from here, there's a rule for it too, right? The sine minus theta is equal to minus sine theta, something like that. This is like, it should not be a problem, really. Okay. Any question? Hello? I don't really want to push the issue very much because I think this is all I want to cover for today. But since we have like 10 minutes, let me start this example to save, oh, not this one, sorry. Let me start this example. You guys have it already, right?
Yes, yes.
Okay. So let us at least give it some designated numbers and so on. So, okay, so that next time we can start right away. And mind you, next time will be 2 weeks from now. So you may forget everything because next Wednesday, it's going to be a holiday, right? And Thursday, if you want to have active class, actually I can come, but I doubt it if anyone will come because tomorrow you should start working on the approximation method. And the last time nobody finished the moment distribution, and then you guys all disappeared as usual. So nothing I can do about that. Okay, yeah. Okay. Now we're going to use the metric displacement method to analyze this structure. And guess what? This structure doesn't have the load. So if I forgot the load in the exam, you could just say everything is 0, right? If you're smart enough, if you notice that. There's no force, no displacement. We're going to have the force here. 60 kilogram force. That's pretty small. Okay. Anything else missing? No, it just accept that E is, this is steel, so it's going to be 2 million kilogram per square centimeter. And area is in the parentheses, and it's in square centimeter. Okay. Area in square centimeter in the parentheses. Okay, that's all we have. Okay, so the first thing that you must be able to do, and you can ask some senior that if you fail to identify the degree of freedom of the system, I am obliged to give you 0 because that's fatal. You are familiar with the word now, fatal. For example, how many degrees of freedom does this truss have? How many degrees of freedom, please? Very well. Okay, I'm not going to tell you now, but let's say we're going to give it some name here. So to have the work laid out for everyone, let us say this is member number 1. This is going to be member number 2. Okay, that's going to be member number 3. You don't have to write in the vertical direction like this. It's up to you. Okay, it's going to be my member number 4. It's going to be my member number 5. You can run the numbers any way you like. Okay, and I'm going to do this for my member number 1. This is going to be my local node 1, 2. And for my member number 2, this is going to be my local node 1, 2. Member 3, that's going to be my local node 1, 2. Now for member number 4, this is my local node 1, 2. And this is my local node 1, 2 for member number 5. Okay. So can you tell me now how many degrees of freedom do we have? Haven't you learned about degree of freedom before?
What about 5?
5, count for me.
The top one for 2.
1 and 2.
Yes.
And
the lower.
Okay.
In the middle.
Okay.
Yeah. And on the left hand side.
The roller on the left.
Yes.
And
in the left support.
What about?
Only 1. Or maybe
Yeah.
2.
Huh? So you say roller on the left hand side, so don't you mean this one?
Yeah, it's correct. But another one, right? I say 5.
Yeah, you said 5.
Yes. 1, 2, 3, 4, and another one will be on the right hand side. Am I correct?
Yeah. Where?
Or just 4? Yeah. For the support.
Where?
The corner. And the right support.
Yeah, what corner?
This corner that you circle is okay. Yeah, this one. Correct.
Yeah. What's the displacement?
Displacement on the horizontal direction.
Here? What kind of support is this?
Oh, okay, I see.
So if you have the horizontal displacement here, what do you have? The whole structure is just gonna slide.
I see. Yeah, I see.
So do we have a rollerblade here or what?
No.
No.
Yeah.
So you see, it's good that you participate. I appreciate that. And you see, if you fail to identify this from the beginning, the rest of your work is garbage. Correct? Because you are heading in the wrong direction. You can never expect to arrive at the right destination. So this guy has 4 degrees of freedom. Okay, so that's going to be the one. So let me call that the Q1. That's Q2. That's going to be Q3. And this guy here, that's Q4. Okay, we still have like 5 minutes left. So I wonder if you could create the local code metrics for the system. Can you do that? Let's try. For example, you can write that way. When you see member number 1, you see it's a node 1, 2 like that. So you see right away that your member number 1, you see member number 1 at local node 1, you can have Q3 and 0, right? So it's 3, 0. And then when you look at node 2, it's a free n, and it's we say here is Q1 and Q2. The reason that we have to put Q1, Q2, 3, 4 like this because we need to share it with every member. You cannot say, okay, it's 1, 2 for member number 1 here, but for member number 3 it becomes something else like 5, 6. You cannot assemble. So we need to give it some name so that we can have the system that belong to each other. So here it's a local node 2, so this becomes 1 and 2. So that's for your member number 1. Can you fill in the rest before we go today? Fire. It should be done in
Yes.
as well. Okay, let's try it, and I'm going to give you the numbers in the end. Are we done? Maybe a minute more. So let's see if you have the same number as I will write down. Okay. Are you done? You guys done? It's not that difficult, is it? So let's say for member number 2 here, you look at the local node 1, you see it's a hinge, so it has to be 0, 0, right? And the local node 2 of member 2, you see Q1 and Q2, so it's 1, 2. For member 3, here, you look at node 1, you see only Q4 in X direction. So here is 4. The no, it's local node 1. Yeah, it's in X. Y is 0, and then another one too. For member 4, you see it's local node 1 here. It's only 3, 0, and local node 2 it's 4, 0. So it's 3, 0, 4, 0. And for member 5, local node 1, 2 like that, it becomes 4, 0, 0, 0. Okay, you have the same code as I do?
Yes, yes.
Okay, so we're gonna do the actions next time. Let's hope that you don't forget anything. If you forget, please do try to review the material before we begin the class next time, which incidentally, it's going to be Wednesday. Huh? Really? Hang on. Let me pause the record. Wednesday after next is the Songkran day, right?